Good evening. Today we are going to see a problem that is on footing, but here we are going to solve the problem that is on pad footing. So difference between a sloped footing and pad footing, that in sloped footing, if you will see, we are going to be in this fashion. So we are going to give slope to it. And then we can have some offset, and footing is like this. Whereas in pad footing, we have directly depth same throughout. And therefore, in this, check for one-way shear and check for two-way shear becomes easy. So now I have considered same problem which we have considered for sloped footing, so that the calculations for till bending moment we have same. So you can see we have now, that is a column carries factorial axial load 1400 kilonewton, and pad rectangular footing for the column ultimate SBC is 225, size of column 300 by 500 mm, M20 and FE415. So we have considered same dimension and same load which we have considered for sloped footing. Now data we have same, so same state. If we will see, I will not go in detail with this. So wherever we have changed, that we will see only. Then we have size of footing, we will be in the same way, no change. So in pad footing and sloped footing, we have these steps same, no change. You can see this, provide size of footing 2.6 meter by 2.8 meter. So area provided 7.28 meters square. Then we have bending moment, we have same. We have to find actual bearing pressure less than ultimate bearing pressure. Bending moment we have along x-axis, we have bending moment along y-y, we have bending moment along x-axis. And then we are going to find out depth from bending moment. So we are here also, we have same step, no change in this step. Now you can see we are going to change this sloped footing to pad footing, and change we have that our pad footing. So we have depth same throughout. So now RU max we will have D, we will get 222.75, again same. Now you can see the change here. We have to consider B, which is 2600. In sloped footing, we have considered it as 400. But depth, if you will see, we are going to provide same, because our criteria of one-way and two-way shear should be satisfied. For that purpose, we will keep depth 500 mm. Sorry, lesser. In sloped footing, we have 600 millimeters. So depth that is going to be reduced. But if you will see, sloped footing is economical because this much concrete we are going to save. But we require skid level for it. Form work is again difficult when we will go for sloped footing. While in pad footing, we have straight form work. Now dx we will get it as 440 millimeter, and now dy we have 430 millimeter. So till this last step, step 3, we have same. From step 4, our calculations are going to be changed. So now my value of dy, this is 430 millimeters. So assuming bar diameter, we have 10 millimeter. Now reinforcement along x direction. So we have calculated it. Now we have value of B. Now here also you can see value of B. We have 2600 into 440 square. Here we have changed. Then B, here we have 2600, and dy, D we have, that is dx. B into dx we have, and value of ASTX. You can see moreover very close values of ASTX, and we have to provide again 28 bar. Then along y direction, if we will go, so formula we have in this way, then value of B, we have 2800 because perpendicular to it. We have YY direction in this way. And perpendicular to this, we have width 2800. This is my Y. And for X, we have this will be X, and therefore my width will be perpendicular to it 2600. And then we have dy 430, we have dy 430, and then we will get this value of by, and that is ASTY 2408 mm square. So this value little bit increased that of last time, because here B we have considered as 2800 millimeters, and then provide 31 bars instead of 28, and for ASTX 28 and for ASTY 31 bar. Now check depth for two-way shear. Now this check depth for two-way shear becomes very easy compared with sloped footing. Now, if in examination not mentioned, you can mention considering paired footing. It's okay, and you can solve it. Now we have critical section is at dyy. So again same dy by 2 from face of the column. And now in this my value becomes 0.3 plus dy by 2 and dy by 2. It will be dy. So it will be 0.73. This is also dy. So this will be 0.93. Then we have perimeter. So again 2 into 0.93 plus 2 into 0.73. So it will be 3320 millimeters. Then we have area at critical section. So we have 0.93 multiplied by 0.73, and it comes 678900. Then you can see here, I will get depth available, and that depth available at critical section is dy only, because we have depth same throughout, and therefore we have to consider this value dy directly. And therefore resisting area at critical section is perimeter into depth. Perimeter is 3320 into 430, and it will be 27,600 millimeters square. Now permissible shear stress we have again in the same way 1.12 Newton per mm square. So this is stress, and stress we have 1.12 Newton per mm square. Now from this we have to find tau UC, and Ks is 1, so it will be 1.12 Newton per mm square. Now shear strength we know, resisting area into permissible stress. Resisting area we have calculated 1427600, and this tau C UC is 1.12, which will give us shear strength, which will be 1598.91 kilonewton. Now we will find shear force, and we have shear force that is actual bearing pressure into area, and then we have this value 192.31 into 2.8 into 2.6. So total area minus we have to subtract area that is of column. So that we have, area that is resisting area, which will be at critical section, and that will be B plus, this is D plus dy, and this will be B plus dy. That area we have subtracted, and that value comes 1269, and shear strength is 1598, and therefore this is same. Then check depth for one-way shear. So we have to go this one-way shear that is at dy from face of the column, and then you can see this critical section. Then we have to find out area of this. For this we require these values of width and depth. So 0.3 into 2 dy, because it is at dy from face of the column, so it will be 1.16, and along depth we have 1.36 meters. So now we have area at critical section, that is, so this distance we will get, that is 0.43 into 2.8. So we have this will be 0.43. And then we have this will be, sorry, this will be 2.8 into dy, not this distance. So we have dy, that is depth at critical section. So 2.8, we have 2.8 into depth at critical section is 0.43. And that will give us 1.204 meters square. Then shear force at critical section, that is actual bearing pressure into shaded area. So this value comes 0.72, that is of shaded area. So this is 0.72 meter. Now how we will get this 0.72 meter? So total we have 2.8. Then we have to subtract from this minus 1.36. And then we have to divide it by 2. We will get this value, that is 0.72 meters. And then 2.6 into 0.72, because BF we have 2.6. And then we have this value 360 kilonewton. Then we will find nominal stress 360 into 10 raised to 3 upon area at critical section. It comes 0.3. So we have percentage of steel along x direction. So 28 bars. It comes 0.38, same as last time. And then tau UC we will get it as 0.42. And we have this value greater than this value. We have 0.3 Newton per mm square. And therefore it is saved. So now last step, that is check for bearing pressure. There is no change. We have to go in the same fashion because it depends upon width of footing and dimensions of column. So that will be as it is. And that permissible bearing pressure 18 and actual bearing pressure 9.33 Newton per mm square. So development length, this is also we have same, and available is greater than required. So likewise, we have to go for pad footing. In pad footing, if you will see, we have mainly change that is in depth of the depth at critical sections. In sloped footing, we have to find depth at critical section. Here we have depth same throughout. So now we will stop here only. Thank you.